So, welcome everybody to this Martin Audio training webinar. My name's Simon Purse. I'll be your host today. I am a product support engineer here at Martin Audio. So it's my job to offer technical support. We do a lot of ease modeling, system design, wiring configurations, anything you can need. You can find any of my or my colleagues' contact details on the website under the support drop-down menu. Yeah, so that's me. So moving on, we are today looking at Display 2.3 with a specific look at using MLA systems within that software. So what is Display 2.3? Display is a free download. You can get it from the Martin Audio website. You have to register for it. There is a tutorial video that comes along with it. It is a proprietary software for our MLA systems, but we also use it with wavefront precision systems, and with the new Display 2.3.1 you can actually optimize our O-line arrays in it as well. And this is a revolutionary and patented approach to array optimization, simply because we work backwards from the audience area back to the arrays, making sure that we get the response we want at the audience area rather than trying to affect the array directly in situ. This software can optimize numerically, as in mathematical and electronic optimization, and it also offers you, also extremely importantly, mechanical optimization, which is optimizing the display angles between the cabinets to give you the optimum acoustical output straight off the get-go. It's really easy software to use. It's a really straightforward workflow, and we're going to go through that in a minute. But it literally is step by step. Fill it all out, and you get various forms of outputs from the software as well, which are all useful in different contexts. The main one of which we will talk about today is the D2P file, which you then upload via ViewNet into your arrays, your MLA system. So there are two user interface modes in Display 2.3. You've got Basic and you've got Expert. Today we're just doing Basic. This is the default mode for Display 2.3, and you can achieve anything you need to do in Basic, to be honest. Expert mode is accessible in the Preference Edit drop-down menu, which you can see in the Settings tab of the software. But for most, I would say nearly all applications, Basic mode will cover absolutely everything you need. So let's move on. The workflow. So the input that we have into this software is venue data. So we're going to draw a two-dimensional slice. So we're going to need measurements. We're going to need we need to know what the venue is. Does it have a balcony? How far we're throwing with the arrays? How high we can throw the arrays, etc. We need to know our sound design objectives. So we need to know, are we trying to avoid anywhere specific, or where our audience is situated, and are they seated or standing? And we also need to know, obviously, our array details. So we need to know, are we using MLA? Are we using MLA compact, etc.? So the workflow, we choose our array. So whatever we've got in the back of the van, we've got 16 MLA compacts. So in this example, we are going to choose an 8-cabinet array of MLA compacts. And then we need to draw a venue slice. So we've now put our array in our venue slice. We then need to define our audience areas, which we will do within the slice and within the software. We can then optimize mechanically our array. So we're then optimizing the display angles. We can then check our mechanical data, so we can check if it's safe or not, whether it's passed various safety criteria. We then optimize the array numerically or electronically. We can then evaluate the entirety of the work that we've done, and we can export an array preset, which is a D2P file, which we then upload into ViewNet. So as you can see, you have an optimized array preset. You can export a mechanical data sheet, so that's going to show you display angles, your max pick height, obviously your safety passes, etc. You can extract a ease data XGLC file, which can be used in calibration with a GLL file to acoustically model and simulate our arrays within the ease software. And you can also export a 3D wireframe, which is a DXF file, which you can use in various AutoCAD software. Well, nearly all of them. I think you can download any of them for free and be able to see a three-dimensional model of that array in that software. So, carrying on. When you first open the display software, you're presented with the dashboard, and you can see that we've got a slice tab. This is where we create our venue geometry and insert a predefined array and also outline our audience areas. In our coverage tab, you go further, more specifically into defining the audience areas in terms of I don't know, offset, whether they're seating or standing, whether we want a +3 or -3 SPL across the venue, where our reference point is, etc. In the display tab, we optimize the array mechanically. So we're also looking at box numbers in that tab and also the array height and indeed its depth position within the slice. The rig tab allows you to check your mechanical data, allows you to see whether it's safe or not. It gives you various other options. The EQ, obviously, we are then optimizing electronically our equalization across the audience area, depending on the variables which we define in the previous tabs. And in the SPL tab, we can then check all of our optimization results and see if we're happy with our predicted end results. So when you first open Display 2.3, you need to add your array. The first thing we do is add the array. So we then click the Add button. And as you can see, you can click on the drop-down menu and you can choose which array you're using. So in this example, again, we're using MLA Compact. So here you can see I've selected MLA Compact from the drop-down menu, and we're going to fly this array. So I click on Fly. And next, on the drop-down menu, I have to choose how many cabinets I've got. I can change this later if I think that my vertical coverage isn't sufficient, or maybe I've gone completely overboard. So I can change this later anyway. So in this example, we're going for 8 cabinets. And I've also named my array, so I've just called it MLAC. But it's a good idea to name your array just in case if you've got, I don't know, various delay towers and outfills and stuff going. It's quite easy to get to lose track of where you are in terms of your two-dimensional slice. So it's always good to name your array something you're going to remember later on. So in our first tab, once we've defined our array, we click on our slice tab. And within this slice, we're going to draw our two-dimensional shell. We're going to then fine-tune it so that we've got the exact measurements of the venue. We can obviously modify or add or remove points anytime. We're going to then add our predefined array, which we've just selected, our 8 boxes of MLA Compact, into that slice. And we're going to tell the software where our audience area starts and where it finishes. So when I click on the slice, I get a little menu pop up, and I can define my maximum height and my maximum length of the venue. Again, we can change this in a minute when we get a little bit deeper in, but it's always good to just straight off the bat get a good sized workspace going. So if we know, for example, in this example, our maximum height is 12 meters and our maximum length is 30 meters, you just type those in, click OK, and away you go. If I've used this venue last week, or if I was working on it earlier in the day and I think, oh, actually, I want to put a different array in there, I can then just choose to load a slice which I've already created. So you don't have to draw anything twice. You could always make, in fact, you could make your own folder of templates if you wanted to. Yeah, so you just load your slice and away you go. But in this example, we're just going to go for a new slice and start from scratch. So this is the slice tab. As you can see, it's blank at the moment because we haven't added anything. But in the top left, we will have a list of vertices, and it will show our X and Z coordinates in space, and we can obviously edit those. The array position below, this will allow us to edit the height and the depth into the room our array is positioned. The survey tab below, I don't know if everybody has this, but if you're using a laser measure, quite often, if you've got a good one, it will allow you to effectively use trigonometry to work out the height of various surfaces. So you don't need to walk all the way around the room to work out the stage height. You can just look at the angle that you're firing down to the bottom of the stage and the angle that you're firing to the top, and you can calculate it from there. But it effectively does it for you. Then we move on to the shell area, and as you can see, the one highlighted is the add shell. So that's the first button we're going to push, but that just allows us to draw our shell in the first place. The other buttons, as we see as we go through this, will allow us to add or take away vertices or whatever we feel like doing. The view button just allows us to effectively make this workbox fit our shell perfectly, so we're not wasting time on calculating large spaces that we're not actually using, and it just generally makes you be able to view your space better. And the array selection of buttons, which we can see next to that, as we go through, you'll see they light up, which allows us to add our array and define our audience area as well. So moving on. So firstly, we need to draw our slice. So you can see in this example, we've got what looks like a theatre with a stage, and it's got a little balcony at the back. So you can just really quickly just go in, always going anti-clockwise, starting from point 1, which is given for you. So we just go, you just click 1, 2, 3, 4, as you go around the room anti-clockwise and draw a very rough, basic shape of your venue. And then this can be refined as we go through. So you can see now this this points box here is now filled with our 10 vertices. As you can see, they're numbered, and they've got all their X and Z coordinates in them. So when we've, I don't know if you've got a CAD file that you're looking at a venue, or even SketchUp, or if you're actually in the venue itself and you're using a laser measure, you can now go through and edit these values for the X and Y of X and Z, sorry, of each of the vertices, and make them as accurate as you possibly can, so that we've got a really accurate model from which to optimize our array. And when we're happy with all of these coordinates, we can move on to adding the array. So as you can see, we're happy with the shape of our venue, and now we're going to add the array. So we literally click on the add the array, and you just drag and drop it in where you think is a sensible location. And then using the array position box, we can then refine these coordinates so that it's exactly where we're going to fly it. So we've got the right height and we've got the right depth into the room. We're then going to add our audience area. So obviously we want our audience to start at the on the floor where the audience begins. You can see it's maybe 3-4 meters back from the stage. If you are using lip fills, suggest you try and use them. So don't try and start your array right at the bottom of the stage, because it's just not going to hit it there. And also it doesn't need to, because you've got lip fills. So always bear that in mind. So we're going to click on the floor, or we click on the add audience area first on this little man here. We're going to click where we want the audience to start, and you literally just move it all the way back and around and stop it where your audience stops. It's always very important as well to remember to click done after each tab, because if you just X off, you might lose some work. So always click done as best practice. So moving on. Now we need to define our audience and non-audience areas and talk about our SPL target. So we click on cover. And as you can see in this, this tab, we've got blue here, which is by default from vertex 1 to 2 is a hard avoid. Then we're moving into the red, which is non-audience, and green, which is our audience areas, and back to non-audience as we go around. And as we go through this, you'll see that all of this is totally customizable. So when we're looking at the audience offsets, so display needs to know where the audience ear height is. Standing uses an average of 1.6 and seated 0.8 meters. If there's a mixture of listening heights, floor standing, balcony seating, etc., then you can uncheck the uniform offset button, which is just here, and this will allow you to place multiple different heights. In fact, even all three if you wanted to. So if you had maybe some people sitting on the floor at the very front, then you had seating, and you had standing at the back, you can do that as and when you need to. So each of these line properties, so when the slice was drawn and audience area was specified, this can now be adjusted by clicking on the type and adjusting the regions where applicable. So now we can adjust, as we go through these, the next few pages, we'll see this, but we can adjust the under balcony as a non-audience area, because obviously nobody from the audience is hanging underneath the balcony. So we don't need to provide high quality, high fidelity, even SPL coverage in this area. So we're going to, as we move through, we're going to change this room so that it's exactly as it appears in reality. So in addition to the audience and non-audience options, there is a parameter called hard avoid. So we apply this when we really want to reduce the level of SPL in any specific location. As you can see, display has automatically placed this area, this hard avoid area, on the stage, as I mentioned, between points 1 and 2. But it really can be anywhere. So if we wanted to get rid of, maybe there's a bit of an echo, a bit of a slap back from the very far wall or even the front of the balcony, then we can tell the array to actively try and avoid placing high levels of SPL in those specific locations. So looking again at the cover still, looking at the audience offset. So now we just need to decide whether these areas here are standing or seating, and also what's going on with the balcony area. So the orange square here highlights the balcony front, and the floor level and ceilings at the back of the walls are currently audience areas, but these need to be changed to reflect the actual conditions, because once again, there is nobody hanging under that balcony, at least I don't think. So the audience offset. So this is currently is saying that everybody in this venue is standing, and we want to change that to seating in this example. So as you can see, you just literally click seating here, or if you wanted seating and standing, you would uncheck that uniform offset button, and then you can highlight where you want to go, and you can just click seating there, and then click or standing on the bottom floor, and just click. But we'll go through that in our example in a bit more detail. So now everybody in this venue is seating, or seated rather. But we still have a few problems with the idea that there's nobody sat on the back wall and there's nobody sat underneath the balcony. So we need to click on our non-audience button right here, and then we can highlight. It's not the dots, by the way. It's the actual grey dotted shell behind that, which we'll see when we do an example. But if we highlight that area, we can then click on it, and it will change from audience to a non-audience area. And again, as you can see, we've gone further again, and we've clicked on non-audience again, and we've gone and highlighted the under balcony area and clicked on it, and now this area is non-audience. And we're actually going to do that again with the front of the balcony. So now we've got seated members of the audience, and then no coverage, and then seated again underneath. And as you can see, this area has actually gone a pink color now, and that literally just means that the array is not capable of producing any direct sound onto this surface. It's in an acoustic shadow, if you like. So moving on, and when we're finished with this tab, we click done once we're happy with this venue. So now we're on the display tab. So in this tab, we're going to adjust array position if we want to. We can change box quantity depending on what the results are, and if we think that they are valid or that they're the best that we can do. And we're also going to optimize the array mechanically. So the cabinet angles. So these are the inter-cabinet angles between each of the array boxes. And they can be changed manually. If you walk into a venue and they've got and anything from our range, it's already up there, and you're not in a position where you can bring the array back down. If you know what display angles are, you can just add them into this tab here, and then you can optimize again electronically further on down the chain, so you can put your own manual angles in if you need to. This tab here in the array diagram shows the actual footprint of the array, and it will update as we go through the optimization process. The window here showing you the coverage, that's what we previously just defined, and it just gives us a pictorial image of where the boxes are actually pointing in space at the moment. But I will say this is a pictorial image, and it is squashed to fit your screen effectively. If you've got a really, really long, thin room, it's going to look a bit squashed up. So it is just a pictorial representation of what your boxes are doing. Below that, we have an acoustic output diagram through what we call an index plot, but I will describe that further as we go through, simply because it's a lot easier to understand when we look at the SPL tab at the end. So in our calculation box here, we've got aim. So aim is the angle of the array determined by the optimization. So this is what the angle of your flying frame effectively. If you've got a 2-point lift, you need to work that out with both your motors. Then that is your aiming angle. Height obviously allows you to move your array up and down through the Z-axis, and the X allows you to move your array in the depth into the room if you need to. So the next thing to do is basically just click the optimize button. And as you can see, that the cabinet angles have now changed in the cabinet angles tab, and we can see the array diagram is now showing us what the array is actually doing in space. And in the coverage tab, we can actually see how the array has splayed itself out to create what the software considers to be an optimum coverage of the space. And you can see the top array is literally right on pointing at the back of the audience, and the bottom array cabinet is pointing right at the front. And that's why it's so important to have either to define your audience areas as either sitting or standing, simply because if somebody stands up, this software is designed then to be basically the HF driver is going to be pointing at their chest rather than their ears, and they are going to miss out on some of that frequency range. We can also see that in the calculation and orientation tabs here that obviously our height and our X coordinates remain the same, but our aim has now changed. So this is the aim that we would want to place our array flying frame at. And once the array is finished optimizing, you can click done, and we move on to the next tab. So now we're looking at the rig tab. So in this tab, we can check our mechanical data, which is like our weights on our front load, our rear load, check it's safe. If it's not safe, it will tell you. We can choose between 1 or 2 rigging points, whether we're flying from the front or the back of the flybar mounting, and we can even choose between ground stacked and flown. So here we are. So you can see that that we have 2 heights actually in the array diagram. Our first height in green here is the very top of the flybar, and our actual height of the array itself is our predefined height that we set, so that's 5 meters. We can again adjust that here if we need to in the mounting options tab. The yellow dot here shows the array's center of gravity. So this is a scaled representation of the array, showing the shape and the top and the bottom of the array relative to the surfaces below, including the distances in the frame here, as you can see. As we can see in the detail diagram, that we can see the top and lower box splay angles. So everything within these 2 white lines is in the coverage area. Then in the mounting options, we can make mechanical changes to our array. So it could be ground stacked or flown if we want to change it. We can change it from a touring or installation frame. We can change it from 1 or 2 point lift, depending on how many motors you've got, whether you want to lift it, actually rig it from the front or the rear of the frame as well. And the aiming angle here, this is again our optimized aim to give us the exact angle that we need to hit that those back audience members. So this displays the calculated array angle plus the angle of the bottom cabinet, which may be easier to measure if the flying grid is not fitted with an inclinometer. So that's just making it easy for you. If you know that the bottom cabinet angle is minus 24.4 degrees, then maybe it's easier for you to measure that. Because if it is 24.4 degrees and you've put all of your splay angles in correctly, then you know that the top angle has to be 5.6 degrees. Next, the loading box just at the bottom there. So that's displaying your total mass, your front load, your rear load, your BGVC1 status, which obviously in this case is a pass, and also your DIN 18800 status, which is again a pass. If any of these failed, they would show in red. You'd also, if the array was unsafe, you'll have a big fail notice written right across the front of the array. So we know that we need to go back and rethink some of the decisions we've made in order to make this array safe for everybody. When you're happy with that, again, we can just click done. But there's a few more. Sorry, excuse me. As you can see from in this mounting options box, is just going through again the fact that you can choose between flown or stacked, between front or rear mounting, or 1 and 2 point lift. It's important to remember it won't let you it won't let you ground stack more cabinets than it is safe to do so. So the software won't let you ground stack or model a ground stacked 16 box array of MLA compact because you can only do 6 with the frames provided. So it won't let you do anything that isn't safe. So it's always important to remember that. But again, once you're finished with this tab, you can click done. So in the EQ tab, now we can set the importance criteria for our audience. So how much effort we want to spend on making the audience area completely seamless in terms of frequency response, or are we more interested in making sure we don't get noise complaints? Are we more interested in our hard avoid areas, or trying to keep the SPL levels down on stage? We can also change our environmental conditions, and after that we can numerically optimize our array, and we can also choose to use or not use our air absorption compensation. So here we go. Again, this is an index plot, and this is something that we use quite regularly in the software. So in this in this plot, if you imagine that our slice has actually been unraveled into a straight line, then this is the stage here. This white dotted line actually shows the start of our audience area. This black line, this black dash line, is showing our reference point, which we saw in that yellow triangle earlier, or we will see in a minute. And this white solid line is actually showing the back of the audience area. And then this will be the back wall and the roof, and then all the way around again. But this, again, will make more sense when we look at our SPL review tab in just 1 minute. So before we electronically or numerically optimize this array, we can also change a few of our environmental factors. So we've got air absorption. Do we want to compensate for air absorption or not? So you can tick this box or not. Obviously, if it's going to be a cooler day, if it's going to be a warmer day, you could even have several of these presets optimized, say at 10 degrees, 15 degrees, 20 degrees. So as it gets warmer throughout the day, you can just keep updating your array, and it will just perform better in these different environmental conditions. So if we're happy with our environmental conditions as it is, we just click optimize, and it will go through the motions. So here you can see this is our predicted response at a range of virtual microphone positions across our audience area. So all those green dots that we saw in our audience area, this is effectively the predicted frequency response at each one of those little points that we saw across the audience area. And as you can see, they're not very tightly packed together. And especially in the HF and even the higher mids, they're looking quite jumbled up there, which has given us a very varied frequency response across the audience area. But after we've optimized and we click this optimization button, you can see how tightly packed they become and how linear they become. And that's basically trying to make it so that at each one of those little virtual microphone positions, we're getting a very, very relatively even frequency response at each of them. So as you move back away from the stage, although the overall SPL drops by, in this case, plus or minus 3 dB, so you're dropping by about 6 dB at the back of the room, you're actually having a very linear response as you move backwards. So your SPL drops, but your fidelity doesn't, effectively. So after that, we can click done, and we can move on to our SPL tab. And this is effectively where we evaluate all of the work that we've just done. So by clicking here, again, this venue slows the slice of the venue that we've been looking at and we've been working with. Audience area in green again, non-audience area in red, and our hard avoid in blue. And the pink here again is in acoustic shadow, so there is no frequency response there effectively because there is no direct sound. This yellow triangle is our reference position, so that was the black dotted line, as you can see in the middle of this index plot here. And this is our cursor, which I will show you in our example that we're going to do in a minute. And this will allow us to check the frequency response in various locations in the room, in fact, all the locations in the room as we move around the venue. In this frequency response chart here, our yellow dotted line as is written on the side here, is our reference position response. So where this little yellow triangle is, the yellow dotted line is the predicted direct SPL response at that location. The white, or the average audience response, is quite hard to see in this particular plot, but that is the average audience response across the entire audience area. So this frequency response graph, shows you from 50 to 16K, all along the x-axis, and with the SPL going up on the y-axis. As we see when we go through the example, the response to the cursor position in the index plot is displayed with its color determined by its region, which is a bit of a mouthful. It basically means when I move this cursor through the audience area, this response is going to be green. As I move it to the back of the wall, when I move into a non-audience area, this is now going to change to a red. If I was to move into a hard avoid area, this frequency response would then be blue, just to show me what I'm looking at as I move across the venue. So the index plot displays the SPL at all positions in the venue as color, so yellow being the loudest running through the color spectrum to blue being the quietest. So the warmer the colors, that is it's a relatively louder SPL level, and obviously the cooler, the quieter it is. So again, the horizontal axis in this frequency and the horizontal axis is frequency, and the vertical axis in this position around is the venue shell. So as if you could follow me through this example that we're going to do next, you'll see that when I move my mouse from the very front to the very back, you'll see this cursor move around the venue, and you'll also see the frequency response change as per the location of that cursor. As we already discussed, the white line at the back here is the end of the audience venue, so this is actually here. This is our reference position, and this is our audience area start. This line here is actually where we're moving through the venue, and that will be the position of the cursor, but we will definitely be revisiting that now. So let's do a live simulation. So let me just get this up. Right, so when you open display 2.3, or in this case display 2.3.1, this is our dashboard. This is the first thing we see. And again, the first thing we need to do is add an array. So as our example said earlier, sorry, this is going to keep jumping onto the other screen, but I'll keep bringing it back. In our example today, we looked at 8 boxes of MLA compact. So let's look at that again. So we click on the drop-down menu, and we're going to choose MLA compact. We are going to fly it. So choose flown. I'm then going to choose 8 boxes, and I'm going to give the array a name. So let's go with MLA compact left and right. And then we click add. So this is our predefined array. And here we go with our dashboard, and we've got all of our tabs. It's very important to remember that we always work from left to right. You don't move on to the next one before you've completed the one before, just because if you work in a logical kind of good workflow in a good order, then you're going to get much better results at the end. So first thing we need to do is draw our slice. So click slice. And then we have this pop-up window. And again, we can just click OK, because we can edit all of this later, or if we want to just get off to a good start, I'm going to say that my venue is 12 meters high and it's 35 meters long. Again, if we wanted to bring up a project that we'd already used, say I was in this venue 2 months ago and I've already got a slice created, I could just load it from a previous file that I've already created. But in this case, we're starting from scratch, so I'm just going to click OK. And then we have our slice window. So I'm just going to maximize that. So here you can see our slice. The first thing we're going to do is draw our shell. So I need to come down here to create a new shell. If there's any button you're not sure about, we've got all these help help buttons that you can click on that will explain the purpose of what it's attached to, or if you just hover over it for a little while, it should tell you what the purpose of that button is. So we're going to draw our slice. So if we click create new shell, and as you can see, this first point is actually done for us. So now I'm just going to draw our stage, and every time I want to drop a vertices, I just left click. So right, there's my stage. I'm going to draw a floor, and I think we'll have another balcony again. So we're going to be in another theatre. So I'm just clicking as I go all the way along, and then when I want to finish, I just right click, and that will close my shell. It's very important you always go anti-clockwise. This is really important for how the software actually calculates what it needs to calculate. As you can see in the points box just up here, now you can see all of the X and Z coordinates for the shell I've just drawn, which is very, very sort of basic and hastily done. But now I can go and I can neaten them up and just refine what I've actually done. So in this situation, my stage is only, I don't know, 1 meter high, and it's 5 meters deep. My floor I'm going to put at 0. My balcony, I don't know, be 4 meters high underneath at the ceiling maybe. And I think the back wall should be, I don't know, 35 meters. Seems good for 8 compact. As you can see, this is now outside of my workbox. So all I have to do is click on this view tab down here, and that will just bring my my slice back into my workbox. Okay, so if I just click that, now you can see I'm back inside. So this is the box from which we do the software does all of its calculations. So we need to make sure that our room is within that box. Let's say our balcony front comes out. Say it starts at 27 meters. It's 27. So that's 4 meters. Let's say that's 5. So it goes up to 7 at the back, and our ceiling is 12 meters. That's at 0. 35, 35. So obviously I've gone through that quite quickly, but I'm assuming that makes sense. It's not particularly complicated. So I've just gone through and neatened all of that up and made sure that it's all as accurate as I can possibly get it. The more accurate you can be, the better results you're going to get. So the next thing I need to do is add my array. So I just click on the add loudspeaker array. And this is our predefined 8 boxes of MLA compact that we've already said we've got. And now we can, in this array position in the bottom left, we can adjust the height and the depth of which this array is positioned in space. So now I'm going to say I'm going to fly it at 7 meters, and my motors are allowing me to position it right above the end of the stage. So it's going to be placed 5 meters into the room. So now that's our array and our slice defined in space. So now I just need to add my audience areas. So I need to add where my audience area starts and where it stops. So I just click add audience region, and I'm actually going to place it 10 meters. So it starts at 10 meters, and I just click and then drag it all the way along, all the way to the end, and then click again. And now you can see my audience area is defined. If I wasn't happy with that, I could just click on this little delete audience area here and then just add a new one. If I wanted to add another point for any reason, another vertices, I can just click on the add vertices there. In fact, I'll put one in now. So just to remind myself of where I started my audience area, I'm just going to put another one in there at 10. And you can see that has now been added to this position here. So that is actually vertices 4. And then we can see it's added a new point for me. So once we're happy with all of that, we can click done. And there we go. So now I need to go onto my cover tab. So I click cover. So again, here is our venue slice. And as you can see, our hard void has been placed deliberately or by default from points 1 to 2, which is on the stage, which is more often than not where you want it anyway. Like I said before, if you wanted to maybe change the front or the back of the room to hard avoid, then you can, and we'll do that in a minute. But in this venue, let's say everybody on this balcony is standing and everybody on the floor is actually seated. So I don't want a uniform offset. So I'm going to untick this uniform offset box. And now you can see I've been given these buttons instead. So this is already standing, so I don't need to change this one. But this floor I need to be seated. So I'm going to click seating. And now I find that I highlight the outline of the shell below the audience area, and I just click once, and you can see this is brought down to seating. And in fact, we've actually got a little issue there, which I'm going to go back and sort out very quickly. So if I just click done, this is because I added that extra point. So I'm going to go back into my slice, move that over here, and I'm just going to going to delete that audience area. I'm now going to click delete vertex. I'm going to delete that vertex, and I'm going to put my audience area back in at 10 meters. Go all the way around. Okay, and we click done. And now we can go back to our cover. I'm just going to reset what I've done. Okay, so once again, we're going to untick this uniform offset. I'm going to click seating because everybody's sat on the floor. And there we go. Now that little clip's gone. So now we've got seating on the bottom floor, but we've also got audience areas on the back walls, underneath the balcony, on the front of the balcony. And we don't really want to be wasting our DSP trying to create good coverage where there isn't anybody there to listen. So we're going to change these areas as well. So we're actually going to click on non-audience. And now I'm going to highlight that back wall. And I'll click again. And now you can see that's turned red. So that's a non-audience area. And I also want this under balcony area here to be non-audience. So I'm going to click non-audience and highlight that area again. That is now non-audience. Also the front of the stage there, I don't want that to be an audience area. So I'm going to click non-audience. And now that is non-audience as well. As you can see, this area is now changed to a pink purple color. And that just means that this array cannot physically transmit direct audio onto this surface. So there is no response in terms of frequency at this area. This is an acoustic shadow at this point. Okay, and once again, this is our reference point. So when we're looking at our SPL, our frequency responses later on, we can actually see the frequency response at this reference point compared to other places, other points within the venue. But if we're happy with this, and I'm quite happy with that, if I wanted to make the ceiling, say it was a particularly reverberant space, if I wanted to make that hard avoid, I can. I just click hard avoid, highlight the ceiling, and change it to hard avoid. But say in this space is actually fine, so it's just going to be a non-audience area. It's easy as that. And then I click done. Okay, so my next tab is display. Okay, so this is our display tab. As you can see, by default, it's just come with 0.5 angles, so that's kind of neutral all the way down the array. But as you can see from our coverage diagram, that's not particularly ideal for the people at the back or the front. It's a bit of an issue, if you like. So we need to optimize this array. And this will optimize based on what we've just told it in terms of coverage. So I need the HF, I need the array to be hitting the people at the front there, and I need it to be hitting the people at the back. So when I click optimize, it's going to work through every possible combination it can to try and create the best acoustic output. So you can see this index plot below is the current acoustic output. The one above is where it's improving it. And it will keep improving it and saving the best one, and then it will try and improve it and save the best one until it thinks it has got the optimal output just from the position of the boxes. So there we go. As you can see, it's because these boxes have a 20-degree dispersion, this is actually going to cover the front. So this is absolutely fine. But we do have an issue in the index plot where it shows us this kind of void going across, and this is just that acoustic shadow there because it cannot measure a surface which it physically cannot radiate onto. So that's why we've got this area here. It's not an issue at all. It's just showing us that we can't actually hit the understage of the balcony. So up in this orientation box here, we've actually got a 3 degrees of positive upward tilt to hit that balcony. And we've obviously used 8 boxes. If I was to use 4 boxes in a situation like this, even if the throw distance was not even half as far, you can imagine that even if all these angles are maxed out, you're going to have really kind of not ideal coverage effectively because your vertical coverage cannot cope with what it's trying to achieve. Even if the SPL is loud enough to make it physically loud enough everywhere, your vertical coverage isn't good enough. So in that situation, you could add more boxes, or if we put 16 WPC in MLA compact, in here, then we might be thinking actually we've put way too many boxes in. Let's try it with 8 and we'll give it another go. So when we're happy with that, you click done. And we're going to go on to rigging just to check if our array is safe. So here is our rigging page. So this is a very accurate model in terms of scale. We can see that our center of gravity is quite nicely in the middle of our array there. Our maximum array height is 7 meters, just like we said. But our actual maximum height, including the frame, is 7.1 meters there, as you can see. The height to the bottom of our array, and remember, this isn't from the stage, this is from 0. So this is from the whatever we call 0. This is how high the array is from that point, so 4.76 meters. So if you're like me and you use a bit of sellotape, some Aleki tape, and you put a tape measure on it just because it's quicker, then you need to make sure you're actually measuring that from the right surface and not from the stage itself. As you can see, in the mounting options, we've chosen flown. We could choose ground stack, but because we've got 8 compact, it won't allow us to do that in this page because it is not safe to ground stack 8 compact. If we had 6, it would allow us to change that. It won't actually allow us to do it in the software anyway. But yeah, just so you know. The frame position, we can change it from rear mounted, and as you can see, the array does not move in space, but the actual frame itself does. So now we can see that it's actually slightly higher just because of the gradient of that. And we're actually doing a 2-point lift, but I know, let's put it back to front mounted. We're doing a 2-point lift. What if I think, oh, one of the motors is broken, I can only do a 1-point lift, so I'll change it to 1-point lift. And now we can see here, it's telling us to do a 1-point lift and use hole 8. Our desired or a designed aim, if we could do everything we can, then we want it to be 3 degrees. But with a 1-point lift, due to the curvature of the array and the center of gravity, the nearest we can get with the holes available is 3.8 degrees. And that's absolutely fine. We can just click use the nearest hole. And now this is shown us in space what this is actually achieving. If I then thought, oh, the motor's fixed, I can put it back to a 2-point lift and we'll just go back to our 3.8 degrees. As you can see on the loading front, we've got our total mass, 440 kilos, and the amount of weight on the rear and front of the frame, so that would be our front and rear motor points. As you see, we've got a BGVC1 pass and our DIN 18800 pass. So this array is completely safe. If it wasn't, you would have fail written in huge letters again right across there, and it would make it abundantly obvious that you shouldn't be flying that array and you should go back and maybe have a bit of a rethink about what's going on, just in terms of the curvature or the angles, or maybe the center of gravity is off for a 1-point lift, etc. Okay, so when we're happy with that, we click done. Now we're on to our numerical optimization in our EQ tab. And again, we've got an index plot here. I don't know, so we're working in Spain today, so it's going to be nice and warm in the summer. I don't know, say it's 29 degrees. So we can just adjust that. Obviously, we can tick our air absorption on and off, depending whether we want compensation or not. Pressure and humidity, obviously, this could change depending on where you're working in the world, but if you do know the humidity level, it really will help your race performance if you can add that in there. But now we're just going to click optimize once we're happy with our environmental conditions. And there we go. And as you can see, these green dots again, they are virtual measurement microphone points, which are placed across our audience area. And as you can see, especially in the HF and like the high and mids, they are quite varied in their results. So you can see up here, I mean, this is 10K, so you're looking at about 15K, something like that up here. This is a huge drop in SPO, like a difference between 80 and maybe 110 to 30 dB difference between one area of the audience area to another. So what we want to try and do is iron all these out as flat as we possibly can using all the DSP and the FIR coefficients that we have available to us. And it's going to try and bring all of those frequency responses close together as it possibly can. And remember, in our MLA systems, you have a separate DSP channel and a separate amplification channel for every single component within each cabinet. So every single HF driver, every single mid, every single low driver is being independently optimized so that it works together in the most optimal performance it possibly can through this software to meet the requirements of everybody in that audience area. So as you can see already in the low frequencies, the frequency response is becoming more and more linear. So although we're getting a drop in SPL from, say, like the very front to the very back, as is physically has to happen due to the inverse square law, but as you can see, it's a very linear reduction in SPL. So we're getting a really even frequency response right across the venue. And as you can see in the index plot above, the hard avoid area, which again we will see and elaborate on in the next tab in our SPL evaluation. But this is the hard avoid area here, so you can see it's quite cool across like nearly the whole frequency band and is improving as our optimization works its way through the audible frequency spectrum. And this is our audience area is also becoming more and more even in terms of a response. And again, our non-audience area on the ceiling it is being optimized as well. So this is optimizing the entire room. It's just showing us the frequency response of our audience area, as you can see from the title of the graph there. If you're using a really large array, say, I know 20 boxes of full MLA or something like this might take 5-10 minutes. So if you do have drawings of the venue or any CAD files that to your disposal, it's always a good idea to try and even get this done before the gig if you can. And then all you have to do is turn up with your DTP export file. Once you've got everything networked on ViewNet, everything's visible, you just load it into your arrays and away you go. It's already optimized for the space. Obviously, all of your angles are already done in the workshop, so you just put it straight up. So it's a very fast and efficient technique, even though the software might take you 10 minutes to get through for each array. That's a lot quicker than moving around the room with a measurement mic, trying to work out if I take 10K out here, does it matter or affect another part of the audience area. And as you can see, even in the high frequencies here, we're really becoming much, much tighter together, getting a much more even distribution across the audience area. And this is optimizing, again, the entire room as it goes. So there we go, and that's a very linear response right across the frequency spectrum and indeed right across the audience areas. So once we're happy with that, which I think we can all be very happy if we had all of our arrays had responses like that. So we click OK, click Done, and now we're going to evaluate our response. Okay, right. So now we can look at this this index plot in a little bit more detail because it's much easier to explain in this window. So again, here is our visual representation of our venue. We've got our audience areas, obviously our acoustic shadow under here, which we can see in this index plot. Non-audience areas, hard avoid, and our, of course, audience areas in our array. In our top frequency response graph in here, you can see this yellow dotted line. That is the frequency response of our reference position. So a virtual microphone in this position will have this response. And our average audience frequency response, so that is just the average frequency response within the audience area, is the white dotted line, which is just under there. And this is accurate in terms of direct SPL to plus or minus 1 dB. So really, really accurate acoustic modeling has been utilized to create this software. As we said in the slideshow previously, that the frequency response will change color depending on the region that you are in. So if we look over here, this is our cursor, this little snowflake here. It's currently in a non-audience area. So this response is red, as this is a non-audience frequency response. But if I move into this index plot, you can see that I can actually move this cursor all the way around the venue. So if I start right at the very bottom, I'm in a non-audience area. I'm in a hard avoid area, sorry. And you can see our frequency response is blue, and it is also dramatically decreased compared to our average response across the venue. And also, if we look here, we can see our cursor is right at the back of the hard avoid area. And if we keep looking in this window, as I move across the index plane, you can see I can move this virtual microphone right the way through the venue, and I can look at the frequency response across the entire venue, all in one straight line. So again, if we're moving forwards, we're in hard avoid, you can see the frequency response is, well, in terms of total SPL, that is going to be significantly lower than when we move into an audience area. And as we come into a non-audience area, we'll see it start to pick up as we move into a audience area. And you can see it is remarkably even straight away as we go in, all the way across the audience area. We're into that black line, so that's our reference point. If I move back, you can see that yellow triangle that we're just about to bump into. That's our reference point. We keep on going, still incredibly linear. Then we're going to hit our back wall. As you can see, it just turns red there for a second, and then we're into an acoustic shadow. So there's no response at all because it's only measuring direct SPL. Then we're back into our audience area, and you can see, again, an extremely linear response. It's just the SPL that drops off at the back, and then we're back to the audience, and we move all the way around the outside walls of the venue. And if we weren't happy with something, maybe actually this wall is a little bit too reverberant, then we just go back into our coverage tab, turn it into a hard avoid, and we just go through that process again, making sure that we do each tab at a time to optimize our array to the best conditions we possibly can. And that's pretty much it in terms of optimizing the array. As you can see, it is an extremely linear response. So if we're very happy with that, we can just click done. We can write some notes if we wish to remind us of what array and what venue we're actually talking about. So then we've got our exports. So we need to actually get this into the arrays. So our first export possibility, you have this little printer here that allows you to print or even just create a little rigging report in terms of a PDF, which will give you all of your splay angles, your array height, whether your weights on your front and rear motors, etc. So you know what's going on. You can just print that off and give it to your rigging guys, or you can use it yourself on stage wherever you need it. The next button we have here is the download for a DXF array file. So that will give you effectively a CAD model of the exact array you created with your splay angles, with the flying frame. Very useful for installations, etc. The next export is a D2P file, and that is what we use in ViewNet. So when we launch ViewNet, all of our arrays are discovered on the network. All of the audio is all set up, and then we just export this file, and we just, using the preset loader, we just drop that file in, and now that array is optimized for that exact venue. And then we have ease 3D data export. Now this, I'm going to click on this just to elaborate a little bit further. So if you use ease, then you'll be familiar with GLL files. But of course, we can't really offer GLL files because every single one of our arrays is optimized for every single specific venue, not only in the way that it looks, but the actual acoustic output of it as well. So every single time you draw an array, then you need to be able to model it accurately. Then you need to be able to export an XGLC file, which effectively calibrates your GLL file within ease. If you need a GLL for any of these arrays, everything but our large like full size format MLA system, you can just click on the show GLLs and it will show you where the software has actually downloaded those GLL files to your computer, so you can locate them within ease. And then obviously go into your GLL setup tab and you can upload your XGLC export file into that.